All right, guys, so we're going to start. First practice problem is going to be question 2 from the 2019 exam, which gives us some times and the corresponding velocities here of some particle moving along the x-axis, and then tells us, the particle is at the origin at time t equals 0, which you can see from here. And then part A asks us, justify why there must be at least one time t on the interval 0.3 to 2.8. Such that the acceleration, which is v prime t of the particle, equals 0. And anytime we do that, anytime we give like some sort of continuum, right, like between here and there, some sort of range, and then we say, the derivative at some point must be this. At least one of the tools in your arsenal you should be thinking about is the mean value theorem. And again, so for the mean value theorem, I'm actually going to get, I got a little animation or a little graphic. Whoops. This was made by the organic chemistry tutor, so shouts out to him. Basically explains that, hey, if you have an interval, that was a word I was looking for before. If you have an interval that's continuous and differentiable, then you have a point on the interval such that, f prime of that point equals the slope or the tangent line of the interval. If you look at this graphic here, it's basically saying that, at some point, if I have this interval a to b, at some point in the interval, the tangent line is going to be the same as the secant line. Pretty cool stuff. So here, the first, we got to first of all explicitly state that that the interval is differentiable and it is continuous, and that is stated. This out of the way real quick. That is stated very clearly in the problem. Get out of here. Whatever, we'll just do that. We'll shrink it. It's not moving. So we could say that it's differentiable because they say it is differentiable, right? And therefore, it must also be continuous, right? So the only thing left for us to do is to apply it. And as we saw in the graphic earlier, right, that's going to be, we're just going to take basically the slope from between these 2 points. And the way we want to think about it is, well, they're asking us to say that the acceleration equals 0. So at what 2 points can we pick here such that the acceleration will give us 0? And you can tell very clearly that that's going to be these two 55s because those are going to cancel out, right? So so f prime of c, right, will be 0 on this interval. And that's going to be, we could do VP1t minus VP2t over 2.8 minus 0.3. That's just going to be 55 minus 55 over 2.8 minus 0.3. And we've pretty much proven the point, right? That you're going to have some point f prime of c on that interval, or some point on that interval c, where the derivative of at that point is going to equal this secant line right here. So in the second part here, they're asking us to use the trapezoidal sum to find the area or take the integral from 0 to 2.8. And these are the 3 subintervals. And for those who might not remember, right, you've got any function, and then you want to take, you want to get the area under the curve. One way to approximate it is to basically chop it up into fine little trapezoids. And so, that might be like a trapezoid number 1, and, your other trapezoid might look like this, and your next one might look like that. And so that kind of finely approximated. So as far as we're concerned, right, we're gonna have 2 heights, and that's going to correspond to the VPT of each interval, and then you're also going to have so those are going to be your 2 bases in the trapezoidal formula, which is base 1 plus base 2 over 2 times height. And then the height is going to be the length of the interval. So for example, for this interval, that would be 1.7 minus 0.3. So we're going to go ahead and write that out real quick. And I'm just going to speed this part up so you don't have to watch me write. Actually, I just went ahead and copied and pasted it from the answer guide because I don't want to, I don't know, there's no reason for me to write it all out. But here we are. So we have each of the sort of I guess you could consider this the height, right? The height of each trapezoid, and that's just going to be 0.3, and then 1.4 to get from 0.3 to 1.7, and then 1.1 to get from 1.7 to 2.8, right? And then we have the different bases here, right? So the first trapezoid, right, this is going to be the height 1 is going to be the first base, and then the height 2 is going to be the second base, and VP of 0 is that height 1, VP of 0.3 is that height 2, and then so on and so forth. And then from there we get to, and so we can go ahead and quickly plug that into our calculator. We get our answer of 40.75. All right, part C tells us that a second particle also moves along the x-axis on the interval of 0 to 4, given by some function right over here. And it tells us find the interval, right, during which the speed is at least, or the velocity is at least 60 meters per hour. And then it says find the distance traveled by the particle over that velocity, over the interval which it is traveling 60 meters per hour in. So the first thing we do is just set this to equal 60, right? So 60 equals 45 root t cosine of 0.063 t squared. And there are, I'm sure, plenty of ways to do this. The way we'll do it is we'll simply plug it into our graphing calculator and then look for the roots, right? Because we could just, so actually first thing we could do is move the 60 over here, so minus 60, and that equals 0 now. And we can now just look for the roots and make our life easy. So we'll just go to the graphing calculator, clicking over here, go to graphing. We'll go ahead and speed this part up. So real quick, on the interval given, I see that the time at which the velocity is going to be over 60, as you can see, is going to be between this point of interest and that, between this neuron, between 1.866 and 3.519. So that's what we're going to write down here, right? So that's going to be our time. Write it like this. I'll include that. And then the second part is to find the distance traveled by the particle during that interval. So we're basically, I'm going to zoom in here so we have more space, right? We're basically going to take the integral from 1.866 to 3.159 of our velocity to get the distance traveled during that time, right? We'll just do it over here where we have some space. So to make our lives easy, we're just going to go ahead and plug this into the calculator. We don't need to solve it directly. So to get this wrapped in integral, just open the parentheses. You can see the little ghost parentheses already closes it for you. So you just type in I and t, and it'll take the integral of the whole function. And we're taking it on the interval from 1.866 to 3.519. There we go. Oh, gotta get rid of that. Minus 60 here. My bad. There we go. 106.109, which is the answer. So part D basically tells us that particle Q is at position x equals 90 at time t equals 0, and then they say, use the information from part B, which is the distance traveled by particle P after 2.8 seconds to see how far P and Q are away from each other. So again, we know P is going to be at 40.75, right? And now we got to figure out where Q is going to be, and that's going to be its initial distance -90 plus the integral from 0 to 2.8 plus the integral from 0 to 2.8 of this function, right? Q of t, sorry, V Q of t. So we can go ahead and plug that in. We already have the information all loaded up in here. So we can just go 0, 2.8, and that's going to give us 135.938, let's call it. It's going to be negative 90. Well, actually, let's go ahead and subtract 90 from that. So negative 90 plus 135.938. That's going to give us 45.938. Now we're finding the different distance from 40.75, so we can go ahead and subtract 40.75 over here. That'll give us 5.188, right? So, you know, P minus Q, or Q minus P, right? We're taking the absolute value. So, equals 5.188. That's going to be our answer. Wow, covered the answer, but okay.